There might be situations in which some of the features in our data set are highly correlated. And the problem with this situation where our features are highly correlated is that it can induce instability into the regression model parameters. This is the idea of multicollinearity. This is going to happen sometimes more often than you would think. Sometimes our features are completely correlated. Can you think of an example in which we would have features that are completely correlated with each other? One thing that might happen, let's say we load a data set, or let's say we download a data set from the internet. Let's go back to the housing prices. Let's say we're trying to predict housing prices. And there might be a feature like the square footage, and there might be another feature that describes the area but in different units, perhaps centimeters squared or something like that. Centimeters squared and the square footage, guess what? Those two features are completely correlated with each other. We may not realize that. We just download our data set and try to use it to train a machine learning model. So this goes to the idea that one of the things you want to do is when you download a data set, start exploring it and try to identify some of these features that are going to be highly correlated. In this situation, those two features will be completely correlated with each other. If we have our data in a pandas data frame, we can use the core method. This core method will return the correlation for our features. In fact, what I'll go ahead and do here is I'll comment some of these lines of code and just study the result of core at the moment. Okay, so using core, we return a data frame, which is going to give us the correlation coefficient for all the pairs of our features. Anything you observe from this data frame of the correlations? One of the things, there's sort of two things you should observe from this data frame, is that the diagonal of the matrix, you can view this as a matrix, is nothing but ones, which makes sense because this diagonal says how well is the median income correlated with median income. Well, the correlation with a variable with itself is always going to be 1. The other thing you need to consider is that the correlation with housing age and median income is the same of median income with housing age. So there's some redundancy in this matrix. So what we really care about is just either the lower diagonal or the upper diagonal of this matrix. So what we're going to go ahead and do here is go ahead and visualize these correlations with a color map. That's what we're going to do in this block of code here. The parts that I'm uncommenting out. And we're going to create a mask to go ahead and mask some of those inputs of our matrix. So we'll use the np_zeros_like function. Basically, the np_zeros_like function is going to take an array and say, okay, construct me an array of this exact same shape. We're going to set the data type in as a Boolean because we're going to use this mask. We want these masks to be true and false values to tell you which entries we should display and which ones should we not display. So we'll create our mask right there. This right here, this function will return the indices of the upper triangle, so we can always just feel comfortable looking at that documentation. So it says return indices of the upper triangle of the array. Remember, with the correlation, there's redundant information. We either want the top part, so the top diagonal or the bottom diagonal. So we'll set those equal to true, and then we'll pass this mask argument when we use this heat map function in this plotting library. Okay, so there is our plotting, our heat map. So this is going to display the correlation of all our features. We can easily see things how we can let's look at some features that are highly correlated. So it makes sense that things like the average number of rooms and average number of bedrooms are highly correlated. It's a subtlety here, bedrooms and rooms. And things like longitude and latitude are also highly correlated as well. But we see some features that aren't so correlated. So let's discuss ways we can fix this multicollinearity problem. We don't want to have features that are highly correlated with each other. So one way we can go about doing this is principal component analysis. So the thinking behind principal component analysis is that let's take our original features. And up to the moment, we've when we've done feature selection, we've reduced some of our original features. Let's say we have 8 features and we drop 2 of them. They're not very important. But let's take a different approach. Let's go ahead and say, let's take our 8 original features, or however many we have, and let's generate new ones. Let's generate 8 new features. And we're going to generate these 8 new features such that they are uncorrelated with each other, completely uncorrelated with each other. And not only that, we're going to create these features such that the first feature, what we call the first feature, is going to try to capture the bulk of the variation, the bulk of the information of our data set. Whatever remains, the second one will try to pick up. Whatever remains, the third one will try to pick up, and so forth down the line. So you have a hierarchy of features. And with this hierarchy of features, you can go ahead and say, I'm going to truncate it maybe from 8 all the way down to 4, and I'll still preserve a bulk of the information of my original features. Now these new features are going to be a linear combination of my old features. So you can think what I'm doing is I'm transforming my data set from one basis, from one set of dimensions, into another. You can view the columns, the features, the characteristics, the attributes of our data set. You can view them as dimensions. You can view our data existing in this high dimensional space. In other words, if we have 3 features, we have points in a 3-dimensional space. If we have 8 features, just like the California housing data set, we have points in an 8-dimensional space. It's hard to visualize it, but we have them in an 8-dimensional space. So principal component analysis is all about generating new features that are uncorrelated with each other. We'll have a whole set of lectures delving into this topic, but we want to first introduce it so we can get a feel for it, such that when we delve more into it, we can get a better understanding of what's going on. So let's visualize what's going on with principal component analysis. So let's go back to that classification scheme, that classification problem that we had. And notice in our task here, when we had 2 dimensions, we were able to draw a line, sort of diagonal, that best separates these 2 classes. But what if I wanted to only use one feature to characterize my data? And what I can go ahead and do is, what if I can generate new features based upon rotating my 2 original features, and I rotate it this way. So let me try to get it exactly down the middle. It's a little hard. That's close enough. So now that I've rotated it, I can generate 2 new features. I can have one feature that goes up and down, that is vertical, and the other feature will be orthogonal to the first feature. And under this method, under this rotation, now I can just only use one feature. I can truncate my feature set such that using just one feature, in this case this vertical feature, will be enough to adequately separate my data. So let me recap what we're doing. We have our points that exist in the original 2-dimensional space. But let's use two other different coordinates. We don't have to use x1 and x2, the original features, but let's generate 2 new features. And those are going to be a rotation. You can visualize them as we're rotating our original space. So now we have one axis that goes this way, that's vertical. After the rotation, the other one will be orthogonal. And these 2 features are completely uncorrelated. Now, I only need one feature to adequately separate the data. Before, I needed 2 features to adequately separate the data. If I only use one, then I would probably do a line this way. And it does okay, but of course I need 2 features to really do a good job. But because of this rotation, we generate a new feature. That's a combination of my 2 old features, and that one should be adequate. Now I set that multiple times. Let's prove it to ourselves. Let's see indeed if we use principal component analysis to truncate our features, to generate 2 new features and only keep one. Let's see how well we do in our classification task. So in import the PCA, since it's going to do some pre-processing on our data set, it's a transformer. So we can view it's going to be one step of our workflow. So here we say PCA one component. In other words, only keep one component. generate my two new features, but only keep the best one. Transform our data set. Let's use logistic regression. With that only single feature, we'll compare it with the old one using two features and look at it here. In fact, it does a slightly better job in terms of accuracy compared to using my two old features. So this is the result of using my two old features, and this is the result of using only one of my new features, which are a linear combination of my old features.